Onida.
Hello, Father Jolie, Disciple. I welcome you. Hello. Hello, Father. Good afternoon.
Good afternoon.
Yeah, I welcome you to this international webinar.
Thank you.
So we can move to a very brief inaugural. All the distinguished participants already joined the webinar. So we can move to a very brief inaugural session before we start with various technical sessions. So over to Ms. Geetu.
Good afternoon, one and all. This program will be recorded and live streamed via our YouTube channel of Christ College IJK. Welcome to RISMA 2021. Recent Innovations in Statistical Methods and Applications International Webinar Series organized by the Department of Statistics in association with IQAC Christ College Autonomous Irinjalkoda as a tribute to our retiring head of the department and controller of examinations, Dr. Davies Anthony Montessori. Your life does not get better by chance. It gets better by change. Let's begin by seeking God's immense blessings.
സത്യത്തിൻ തത്വമേ നീലസിപ്പൂ കാണായവക്കെല്ലാം കണ്ണിൽ പൊരുളായി കാണപ്പെടാതെ ഇരിക്കുവോനേ ഞാനൊരു മൺതരി മാത്രമാണെങ്കിലും നൂനമവീടുത്തെ സൃഷ്ടിയല്ലോ കൈവിടാതെന്നെ നീ കാരുണ്യകാതലേ കൈവല്യദാതാവേ കൈത്തൊഴുന്നേൻ കൈത്തൊഴുന്നേൻ കൈത്തൊഴുന്നേൻ.
It's the time to formally welcome you all. I invite Dr. Sister Mariama, General Convener of this webinar, for welcome address. Over to you, Sister.
Respected dignitaries, Reverend Father Jacob Nyerinyambilli, our manager, Reverend Dr. Jolie Andrews, our principal, eminent resource person of the day, Dr. K. Jayakumar, Professor Ankit, Department of Statistics, University of Calicut, Professor David Hanagal, Department of Statistics, Savitri Bai, Pune University, Dr. Robinson Palmadisheri, IQAC Coordinator, respected dignitaries, Reverend Father Jacob Nyerinyambilli, our manager, Reverend Dr. Jolie Andrews, our principal, eminent resource persons of the day, Dr. K. Jayakumar, Professor and Head, Department of Statistics, University of Calicut, Professor David Hanagal, Department of Statistics, Savitri Bai, Pune University, Dr. Robinson Panmanisheri, IQAC Coordinator, Dr. Davis Anthony Mundasheri, Head of the Department of Statistics and Controller of Examinations, esteemed participants, and my dear colleagues. A warm good afternoon to one and all. Recent innovations in statistical methods and applications, RISMA 2021, is organized as a tribute to our retiring head of the department and controller of the examinations, Dr. Davis Anthony Mundasheri, a dedicated, sincere, and vibrant personality. This webinar offers collaborative platform for sharing recent innovations in statistical methods and applications by renowned resource persons from all over the world. With this short introduction about the webinar, I come to the duty entrusted on me. To begin with, let me extend a heartfelt welcome to our respected manager, Reverend Father Jacob Nyerinyambilli, for accepting our invitation to inaugurate this webinar. We are greatly encouraged by your gracious presence and support. Welcome you, Father. It is a glorious moment to extend my warm welcome to our dear principal, Reverend Dr. Jolie Andrews, who is a strong pillar and an efficient leader, guiding Christ College in its way to success. He has always been supportive towards all the good initiatives taken up by the department too. So, with great pleasure, I use this opportunity to welcome our dear principal, Reverend Dr. Jolie Andrews, to this function.
Thank you.
I would like to welcome the distinguished resource persons of the day, Dr. K. Jayakumar, who is reputed as very systematic, highly intellectual, and outstanding research-oriented. Sir has kindly set aside all his other engagements and consented to deliver knowledge-packed session ahead. I am also happy to say that he is the research guide of our dear Dr. Davis Anthony Mundasheri. Welcome you, sir. Now I would like to welcome Professor David Hanagal, Faculty of the Department of Statistics, Pune University, as a resource person. We feel extremely privileged to have you with us and are excited for an interactive session. Welcome you, sir. Next, I would like to welcome Dr. Robinson Panmanisheri, IQAC coordinator, who is always a strong guidance and support for all the activities of our department. I express a cordial welcome to you, sir. I also welcome all reputed persons of the webinar joined with us in this inaugural session. A warm welcome to all the faculty of Christ College and various institutions, research college, and all other participants joining us in this inaugural session. Last but not the least, I wish to welcome all my dear colleagues and students. Once again, welcome you all. Thank you.
Thank you, sister. With immense pleasure, I invite our beloved principal, Reverend Dr. Jolie Andrews, the ever-inspiring force, to give away the presidential address. Over to you, Father.
Good afternoon. I think you can all hear and see me.
Yes, Father.
Thank you. Reverend Father Jacob Nyerinyambili, the most respected and beloved manager of Christ College, Iringalakota. Dr. K. Jayakumar, the research guide of our beloved Dr. Davis Anthony Mundasheri, who is also the professor and HOD of the Calicut University. Dr. Davis Anthony Mundasheri, the controller of examination and HOD of the Department of Statistics, on whose honor we are having this international webinar on recent innovations in statistical methods and applications. Dr. Robinson, the IQAC coordinator. Reverend Sister Josephine, who is the host of the program and the general convener. Reverend Dr. Sister Mariama Kedi, who is the general convener of this program. Ms. Megha CM, who is the coordinator of this program. All the faculty members from the college, from the neighboring college, research institutes, and research students. Indeed, it is a very happy privilege to have this international webinar here, RISMA 2021, on the recent innovations in the statistical methods. We know that today's technology is the technology of using the statistical tools in different realms of science. Today's science is a science of big data. You got immense data with you, but you should be able to process this data in a systematic manner. And here we come, this RISMA 2021, to shed new lights as far as the different tools which the statisticians can offer to the different areas of the research. Especially congratulate the Department of Statistics in a very, very special manner for organizing this international webinar. We are having speakers not just from India, even from abroad. I also take this opportunity to, in a very, very special way, to thank Dr. Davis Anthony Mundasheri, our beloved controller of examination, who was dedicated, I would say, immensely by his hard work, dedication to the Christ College, because Christ College Iringalakota is, I would say, the largest autonomous college in Kerala. As far as the student enrollment is been concerned, we have got now 4,454 students now. And this is the largest college as far as the student enrollment has been concerned. And I would say it is a Herculean task to conduct the examination of all the different departments in this college in a very meticulous, I would say, systematic and an efficient manner. And a statistician has come forward to take this lead from the time onwards, of course, after 1 year from the date of being an autonomous college. So a big salute to our Dr. Davis Anthony Mundasheri, on whose honor we are having this webinar in a very, very special manner. My special appreciation to every one of you who are participating in this webinar. May this interaction help us to come forward in the statistical research in a new and vigorous manner. May God bless you all. Have a wonderful day. Thank you. Thank you so much.
Thank you, Father. With heartfelt ovation, I take this opportunity to invite Dr. Davis Anthony Mundasheri, Head of the Department and Controller of Examinations, who is constantly supporting and guiding us. I kindly request you to introduce RISMA 2021 and speakers of the day. Over to you, sir.
Respected Reverend Dr. Jolie Andrews, CMI, President of this inaugural session and Principal of the College. Reverend Father Jacob Nerinyambili is my Manager of the College. Dr. K. Jayakumar and Dr. David Hanegal, Resource Persons of the Day. Dr. Robinson Panminisheri, IQC Coordinator, and all other resource persons, teachers from various colleges, participants, and my dear colleagues. A very good afternoon to everyone. I am very happy to introduce this webinar on recent innovations in statistical methods and applications, RISMA 2021, organized by the Department of Statistics, Christ College, Calicut. In today's society, technology has become more advanced than humans' mind. As the role of technology becomes multifold in every sector, it generates huge amounts of data that can yield valuable insights. The increasing demand emphasizes the importance of more and better statistical methods and its application. Recent years witnessed the emergence of modern methods in statistical analysis and a dramatic increase in computational techniques. This importance of the subject is the motivation for us to bring together many reputed and internationally well-known resource persons to share their experiences and contributions in a common platform. I am very happy to say that we have received 300 plus registrations from various reputed institutions in India and also from abroad, like Nigeria, Philippines, Saudi, Zululand, Kuwait, etc. We hope that all the deliberations and discussions in various technical sessions of this webinar will definitely impart huge information to all participants, and wishing you all a very fruitful days. Let me introduce the speakers of the day. We have two technical sessions on today. One is by Dr. K. Jayakumar, Head of the Department of Statistics, University of Calicut, a very dedicated, enthusiastic teacher and a researcher. His area of research is distribution theory and time series analysis. He has received many awards and honors like NBHM Postdoctoral Research Fellowship, Jan Timmergen Award of International Statistical Institute, Netherlands, Best Research Paper Award of papers published in ISI-cited journals of King Saudi University, etc. He has 100 plus research publications in his credit, which include Journal of Applied Probability, Statistics and Probability Letters, Communications in Statistics, Journal Statistical Simulation and Computation, Applied Mathematical Letters, etc. He is a very familiar figure in many national and international conferences as a resource person. He is a reviewer of many internationally reputed journals like SPL, then JMA, etc. I am very delighted to introduce him today to this webinar, even personally, as he was my research supervisor. He will talk to us on sub-exponentiality and integrated scales. We have a second session by Dr. David D. Hanegal. He is the professor and head of the Faculty of Science, Vishwakarma University, and former professor and head of the Department of Statistics, Pune University, Pune. He was an elected fellow of Royal Statistical Society, London, UK in 2003. He has more than 40 years of very active teaching and research experience in inference, in bivariate and multivariate exponential distribution, surveil analysis, frailty models, etc. He has received many appointments from various reputed universities of Mexico, Germany, USA as a visiting professor. He is the author of 100 plus international publications with nearly 1,800 Google citations and very good impact factor. The books written by him were published by very reputed publishers like Stale and Francis. He is referee of various journals like Communications in Statistics, Biometrics, Statistical Purpose, and so on. He is a life member of many national and international academic. He has delivered talk in more than 50 international conferences and have undertaken many research projects funded by various national and international universities. Today, he will talk about positive, stable, shared frailty model based on additive hazard. Once again, wishing all the participants a very fruitful and informative sessions in this RISMA 2021 webinar. Thank you.
Thank you, sir. As a token of love, I kindly request all the distinguished participants to switch on your videos for a while. To follow with, I now call upon our manager, Reverend Father Jacob Nyirinjamili, the benevolent spirit behind all the activities of Christ College, to render the inaugural address. Over to you, Father.
Good afternoon, everybody. Hear me?
Yes, Father.
Principal, Dr. Jolly Andrews, Dr. Davis Anthony, controller of examinations, and the man behind this internet webinar, IQAC coordinator, Dr. Robin sir, all the staff members of statistics department, today's eminent speakers, Dr. K. Jayakumar, Professor and Head of the Department of Statistics, University of Calicut, Dr. David Hanagal, Department of Statistics, Pune University, and all the participants attending this international webinar. I am very happy to hear that Statistics Department is conducting a webinar to honor Dr. Davis Anthony Mundasheri, Head of the Department of Statistics and Controller of Examinations of Christ College. It is a tribute to Dr. Davis Anthony because he is such a hardworking man. He is in the college doing his duties till 10, 11, 12 at night. He is such a responsible person, spending sleepless nights for Christ College and his students. He is so gentle in his character and duty-bound, very sincere and charming fellow. Very difficult to see such a personality in our life. Surely, in this way, it is really a tribute to Dr. Davis Anthony. I especially congratulate the Department of Statistics for conducting such a webinar, international webinar, especially Sister Dr. Mariama, General Convener, and Mega CM Coordinator, and all other faculty members. All the best wishes, and I formally inaugurate this international webinar. Thank you. Thank you.
Thank you, Father. It's my privilege to invite the IQAC coordinator, Dr. Robinson Ponminisheri, the indomitable pillar, to felicitate the event. Over to you, sir.
Thank you, Guido. Respected dignitaries and participants of this webinar, I have great pleasure to address this international workshop on recent innovations in statistical methods and applications, which is also a tribute to Dr. Davis Anthony. Our manager and principal already detailed about his contributions to the college. Here, I would like to mention about his contributions as a personal mentor to me. When he was the IQAC coordinator, I always wondered about the tremendous hard work he was doing towards the accreditation process. I had a wonderful opportunity to work with him, and the training given by him was very excellent. I remember one instance in the year of 2013, when we were planning a workshop on intellectual property rights. I was the convener of the program, and I had a very serious issue at that time at home, and I couldn't come for a couple of days. When I informed Dr. Davis, he told me, Robinson, you don't have to worry about anything. He will take care of everything, and to just come for the inauguration session for the welcome speech. I was so surprised by his words, and that happened also. And he has been always a support to me as an elder brother. Dear my brother, Dr. Davis sir, wish you all the best in your retired life. And
Sir.
for organizing the webinar, which is comprising of 12 eminent speakers. Also, I would like to mention the contribution of Department of Statistics in the form of an online foundation course in R programming, which is taken by all the students of University of Calicut. I wish a great success to this webinar, Department of Statistics, and all the participants. Thank you.
Thank you, sir. With immense gratitude and happiness, I call Ms. Megha CM, the untiring coordinator of this program, to propose a vote of thanks. Over to you, ma'am.
Thank you, Gitu. Respected dignitaries, Reverend Father Jacob Nyirinyambili, our manager, Reverend Dr. Dolly Andrews, our principal, eminent resource persons of the day, Dr. K. Jayakumar, Professor and Head, Department of Statistics, University of Calicut, Professor David Hanagel, Department of Statistics, Savitribai Phule, Pune University, Dr. Robinson Ponminisheri, IQAC Coordinator, Dr. Davis Anthony Mundacheri, Head of the Department of Statistics and Controller of Examinations, esteemed participants and my dear colleagues. A warm good afternoon to one and all. It is my privilege to have been asked to propose the vote of thanks for the inaugural session. To begin with, let me extend our sincere gratitude to our respected manager, Reverend Father Jacob Nyirinyambili, for inaugurating this webinar. Thank you, Father. Next, I would like to thank our principal, Reverend Dr. Jolly Andrews. He acted as a catalyst that stimulated us to do our best. Thank you, Father, for your presidential address. Now, I would like to thank Dr. Robinson Ponminisheri, the IQAC coordinator, who constantly support and encourage us in all our endeavors. Thank you, sir, for felicitating RISMA 2021. Also, I would like to express our sincere gratitude to Dr. K. Jayakumar, who extended full support in organizing this webinar. With his guidance and suggestions only, this event could be materialized. I'm thanking you for your support and your presence in inaugural session. I also thank Dr. David Hanagel for his participation in the session. I thank all resource persons, teachers from various colleges, research scholars, students who joined us in inaugural session. I express warm gratitude to all the teachers of our college and the students joined in this inaugural program. Last but not the least, I also extend my sincere thanks to the entire team behind RISMA 2021. Thank you. Have a nice day.
Thank you, ma'am. Formal inaugural function has come to an end. We now move on to our first technical session led by Dr. K. Jayakumar, Professor and Head, Department of Statistics, University of Calicut, on the topic on sub-exponentiality and integrated tails. I invite you, sir. Sir, please.
Good afternoon to all. First of all, I am very happy to see that the Christ College is organizing such a webinar on the eve of kind of descending in the city. And first of all, I thank the Department of Statistics department, and I wish the department I directly go to the topic. The topic of today's discussion is exponentiality and integration. So, you know, visible to everyone? Is it visible?
Sir, your voice.
Yes, sir. Visible. Visible. Yes, visible.
Slide is okay, but
Voice
your
is
voice
also
okay.
audible.
Okay.
Voice is audible.
Okay. So the talk is on sub-exponentiality at integrated tails, and it mainly the talk mainly concentrates on heavy tail distributions. And sub-exponentiality is a property that is associated with the tail behavior of certain distributions. As we all know, the distributions are in fact essential for modeling real data sets. For modeling the data associated with random experiment, we need different types of distributions. And one class of distributions that is, in fact, of particular use is the sub-exponential distributions. So I may just go into the technical details of this distribution. So suppose we have a distribution function f with the mass at 0, it is 0, and the fx is less than 1 for every x in 0 infinity, with and f of infinity is equal to 1. And we know that the distribution is in the class of the sub-exponential if 1 minus f convolution of f is in fact asymptotically equivalent to 2 into 1 minus of f of x. So what does it mean? So you know that f convolution f, you may be able to think of it as the distribution of the sum of two random variables. In fact, two independent and identically distributed random variables, each has the distribution function f. So I have considered two random variables x1 and x2, and these two random variables are independent, and they have the common distribution function f. Then the distribution function of the sum x1 plus x2 is nothing but f convolution f of x. Now what does it? 1 minus f convolution f of x. That is the tail of the distribution corresponding to the sum x1 plus x2. That I may be able to approximate by 2 into the tail of one random distribution of a single random variable. So the distribution of x1 plus x2, the tail of the distribution of x1 plus x2, I may be able to approximate as, or I may be able to write it as 2 into 1 minus f of x. That is 2 into twice the tail of a single random variable. So, or another way, let x and x2 be IIDF, then probability that x1 plus x2 greater than x, that is this one, that is 1 minus f convolution f of x. That is in fact equivalent to twice probability of xn greater than x. So or another way, limit x tends to infinity, f bar convolution x by f bar x is equal to 2. So a natural question is that, does these things arise in real life situations? So you can see that in my discussion, you may be able to see that there arise a number of situations where I may be able to come these situations. For example, in modeling the risk associated with insurance, queuing theory and all that. So the concept you may be able to, so this concept I have expressed for, or we have defined in terms of two random variables, and you may be able to extend it for a finite number of random variables n, and in that case you may get that, so in that is the enfold, the tail of the random variable x1 plus x2 plus etc plus xn, you may be able to approximate as n into the tail of a single random variable. So in that case, you may be able to tell that the distribution is sub-exponential. So, and now, what is the implication of sub-exponentiality in general? So the concept of sub-exponentiality tells that the sum of large numbers of random variables, I may be able to approximate by the extreme random variable, that is the maximum. So if suppose you have to know about the behavior of xn plus x2 plus etc. plus xn when n large and x is large. So in that situation, you may be able to approximate the distribution of the sum by the distribution of the maximum. So that is the advantage associated with sub-exponentiality. So you may not be, in some situations, you may not be able to identify the distribution of the sum in a proper way, or it may not have a closed form, or the calculation of the distribution of the sum becomes difficult. So if you may be able to identify that your distribution, if you may be able to identify that your distribution is in the class of sub-exponential family, then what does it mean? You may be able to, you can see that the distribution or the, in fact, the tail of the distribution of the sum is nothing but it is, in fact, asymptotically equivalent to the distribution of the maximum. So that is, in fact, the advantage of sub-exponentiality in dealing with sums of random variables. And we know that in the study of distributions or in the study of random phenomena, we may come across large numbers. Or in other words, you may be able to deal with the sum of a large number of random variables. The question is whether you may be able to find the sum of the larger number of random variables, or probabilistically, how we may be able to deal with the distribution of the sum. And you can see that even though when you are adding a number of terms, for example, positive terms, you may be able to see that the sum should diverge. But the theory tells that under proper normalization, so if you are normalized that sum, then you may be able, or in other words, you may be able to scale down each of the contribution of single random variables to the sum in such a way that the sum will converge. Then we may be able to talk about the random phenomena in a more appropriate way. And that is in fact the essence of what is known as the central limit theorem and associated with the central limit problem, the associated central limit problem. And okay, so or in other words, you may be able to discuss or describe the distribution of the sum by the distribution of the maximum in the sub-exponential case. And one of the distribution when we are associated with the renewal process and some types of events is nothing but it is the integrated tail distribution. So the one who has studied the renewal process, which in fact describes the in fact it will describe the waiting time associated with a given process. So you may, in that case, we may have come across the integrated tail distribution, and the integrated tail distribution is defined by f1 is equal to 1 by mu integral 0 to x f bar by dy. So you are in fact, what is the tail of the random variable x? If you have the random variable x distribution function f, then the tail is nothing but your f bar y or f bar x. Then what is the integrated tail? That is 1 by mu integral 0 to x f bar y dy. And you can see that there is a one-on correspondence between your f and the integrated tail f1. And once you have established the sub-exponential property of your f, you may be able to identify the tail behavior of your f1 also. So that is the advantage that you have. And now I may look for the theoretical aspects of the class of sub-exponential distributions. And you can see that all sub-exponential distributions are long tail. So I may define what do you mean by tail. So I will define the number of concepts that is associated with the tail of a distribution. So one is the heavy-tailed behavior, other one is the long-tailed behavior, and the class of dominator variation distributions, and so on. And you can see that all sub-exponential distributions are long tail, and the converse need not be true. So we can see a number of examples. So what is a long-tailed distribution? Long-tailed distribution is nothing but, so let me denote the class of long-tailed distribution with L. What does it mean? So it means that probability that x greater than x minus y is, in fact, you may be able to approximate as probability that x greater than x as x tends to infinity for every y real. Right. So for every y real, so you may be, whenever your x is large, you may be able to tell that the tail of x minus 1 is the same as the tail of the random variable x evaluated at the point x minus 1 is the same as the tail of the random variable x evaluated at x. And the tail of the random variable evaluated at x minus 2 is same as the tail of the random variable evaluated at x, and so on. So that is in fact a desirable property as far as a practitioner is concerned, because he is in fact sometimes interested in the behavior of your tail of x, but he may be able to approximate that tail by the tail of the random variable x evaluated at x minus y. And whenever your x becomes large, the probability that x greater than x minus y by probability that x greater than x is equal to 1, then the class of the random variables that or distributions that having that property you may call as the class of long-tailed distributions. And so one of the what is its implication? You can see that. So the implication I have already told, and in that case, you may be able to tell that your limit extends to infinity, hx is 0. What is it? Hx is the hazard rate of x. What does it mean? Hx, hazard rate means that the instantaneous failure rate. What is instantaneous failure rate? That is a lifetime component that is in fact functioning very efficiently. And you are in fact estimating the probability of sudden failure of that component. So the probability of the sudden failure of a component which is functioning, that probability that you may call it as the instantaneous failure rate. So that is the instantaneous failure rate. And the L-class distributions, the class of long-tailed distributions has the property that limit extends to infinity hx is 0, which means that the hazard rate, the instantaneous failure rate becomes 0 as x is large. So which you may be able to see that it is not from a desirable property from a practitioner. Even though it is a desirable property, but you may not be able to give sufficient interpretation for that, because your consciousness usually tell you that as time becomes large or the life becomes large, more and more the probability of instantaneous failure is larger and larger. That may be. But in the case of L class, you have the converse is true. So that is the interpretation of that. And whether is it you may be able to see any distributions this property possessing this property. That is a natural question. And you can see that you may be able to identify a number of distributions that you use in commonly as this property. That is, limit extends to infinity hx is 0. And I will look into the examples of these classes later. And another class of distribution that is of interest is the class of dominated variation tails, which tells that the tail behavior of the random variable x evaluated at x divided by the tail behavior of the random variable, the tail of the random variable x evaluated at 2x. So that ratio is finite whenever x is large. So, and what is the role of sub-exponential distributions in this? You can see that sub-exponential distributions is a member in between this one, this D intersection L and L. So you can see that D intersection L, what is your D? The class of dominated variation tail distributions, which I have defined now. And what is your L spectral? It is the class of long-tailed distributions. So the intersection of dominated variation tail distributions and a class of long tail distributions. There you can see that it is a proper subclass of the classes of exponential distributions, which in turn is a subclass of, that is again a proper subclass of the class of long tail distributions. That is in fact the inclusion relation between the script D, script L, and script S. And you can see that all sub-exponential distributions are heavy tail, and the converse may not be true. There's a similar assertion I have already told in terms of in the case of long tail distributions. So all long tail distributions are sub-exponentials. So all sub-exponential distributions are long tail, but the converse may not be true. Here also, all the sub-exponential distributions are heavy tail, but the converse may not be true. Now, what is a heavy tail distribution? What is a heavy tail? So you can see that that is a property associated with the exponential tail. So, or in other words, you may say that a distribution has heavy tail if the tail of the random variable x is bounded by exponential tail. So, or in other words, here, if the tail of your distribution is more as compared to the tail of exponential, then you will say that the distribution is heavy tail. So, how will you show graphically? So, a distribution with a tail that is heavier than exponential is called a heavy tailed distribution. A distribution with a tail heavier than exponential is called a heavy tailed distribution. So, for example, you just look at the graph. You have your exponential graph is in the blue line, and another graph which is in the red one, that is, you can see that the tail of that is above the blue line. So, the tail of that is above the blue line means that the tail is more than that of the exponential one, so that this distribution is heavy. So that is the definition of heavy tail. So you can see that the Pareto distribution is classified as Pareto type 1, type 2, type 3, type 4, and so on. What I am talking about here is that the Pareto type 1 distribution. So the Pareto type 1 distribution is in fact a heavy tail distribution. Pareto distribution is in fact useful in a number of cases. For example, the distribution is in fact useful is in fact income modeling. Income modeling means that what does it mean? Income model means that if you may be able to model the distribution of income of individuals in a particular country, you may be able to use the Pareto distribution, and you can see that it is in fact useful for modeling the income distributions in a country like us, where you can concentrated on number of people. So you may be able to see that there is an unequal distribution of income. So if there is an unequal distribution of income, you may be able to use the Pareto distribution as a proper choice for modeling that income phenomena. And you can see that Pareto distribution is in fact a heavy tail distribution. Very well applied in in fact, no heavy tail. How does this details come across? What does it mean? Why the graph behaves like this? If you draw the behavior of a distribution, a natural question is why the graph behaves like this? What's the reason for it? Is there any particular reason for it? Or why this tail is significant? Or what does this tail mean? So if you look into the details of it, you can see that it in fact tells that the distribution, the data is in fact dispersed very more and more. Oh, and you can see that what is your dispersion. You know, you have studied standard deviation or variance, mean deviation, quartile deviation, etc. So the dispersion is more means that the distribution of data sets within themselves and the distribution of data sets from the mean, you can see that it is very large, which means that the data is scattered around. It is not concentrated around the mean, but it is scattered more and more. The data is scattered more and more. So since the data is scattered more and more, the tail of the distribution becomes significant. So such a case, you may come across a heavy tail distribution. So in such a case, we may come across a heavy tail distribution for modeling data. So that is the interpretation. So that's okay. And you can see that examples of one-tailed distribution. So you have come across one-tailed distributions or two-tailed distributions. And one of the one-tailed distributions include log normal, Levy distribution. In other words, it is called stable distribution. That it is in fact positive stable. Positive stable with index of stability, you have it is equal to 1/2. The index of stability of a positive stable random variable, when it is 1/2, you may come across what is known as the Levy law. And now you have the third system of distributions, log logistic, log gamma, Weibull, log Cauchy. All those things are in fact heavy tail. All are heavy tail distributions. And you can see that all these distributions are commonly applied in a variety of fields, not necessarily in statistics, fields in biosciences, economics, in every branch of knowledge. We may use these types of distributions. Which means that for modeling data sets where the data set has a departure from the mean and the scattering of the observations are in fact very, very wide, you can see that in most of the situations, in such a case, you may have the mean becomes, mean is in fact, what is it? The mean is in fact becomes very large, or it may tend to be infinite. So such a situation, you may come across what that is situation where one may suspect of heavy. And there are other situations, this is a situation of one-tailed distribution. Now let me look for two-tailed distribution so that you have the, in that situation, then what are the tails? The tails of a two-tailed distribution is, it has two tails. One tail is probability that x less than or equal to minus x, that is the lower tail. And the upper tail is probability that x greater than x. So it has two tails. One is probability that x less than or equal to minus x, that is the lower tail. And the upper tail is probability that x greater than x. Now, to study the behavior of the distribution model of such a distribution, may have to know the probability that x less than or equal to x plus probability that x greater than x, or you have to study 1 minus f of minus x plus f of x. That is the tail. And the examples of two-tailed distributions that are heavy-tailed are the Cauchy distribution, stable distribution, student Q distribution, etc. All these things are heavy-tailed. And what are the index properties of heavy tail distributions? The heavy tail distribution, I have already told that Pareto distribution is in fact a heavy tail distribution. And you know the Pareto principle. That is it. You can see that, for example, the 80% of wealth is owned by 20% of population. That is, the most of the income is concentrated on less number of people. So if that is such an inequality, you have studied Lawrence curve and income inequality. if you have well versed with economics and so on, or in, you have studied it. So in such a case of modeling these inequalities, that is the disparity from the line of equal distribution, you may be able to use, that is the Pareto distribution and log normal distribution is a particular, is a proper choice. And you can see that in the Pareto principle situation, you may come across infinite variance, or you may come across even infinite mean. So why it is so? I have already told that is the observations has a departure from the measure of central tendency that you have. And events are much larger than mean happen. That is, events that are much larger than mean happen frequently. Right. So in that case, the variance becomes significant and the tail becomes more and more significant. That is the situation. So that is in such a situation, you may not be able to model the data sets with the conventional distribution. So you can see that if you are a practitioner, you may be able to view it very clearly. And these things, now, how we study the behavior of these heavy tail winners? And there are three fundamental principles dealing with these heavy tail winners. And that is tail invariance, catastrophe principle, and the blowing nature of residual life or the remaining life. So these three indicate the heavy-tailed phenomena if we inherited in or exhibited in a data set. Now what is scale invariance? Now a distribution of scale invariance, if there exists an x known and a function g such that the probability that or f bar x lambda x, f bar is nothing but it is a survival function. The f bar lambda x is equal to g lambda into f bar x for all lambda x such that lambda is greater than equal to x naught. So in such a situation, if you have such an f, you may call it is scale invariant. And you can see that it is a characterizing property of the Pareto distribution. So, or in other words, you have this result. A distribution is scale invariant if and only if it is Pareto. So that is in fact the property of the Pareto distribution, and it is because of this the Pareto distribution is widely applied in various fields of heavy-tailed data modeling, especially in and you can see that f bar lambda x is what is your f bar x? F bar x for Pareto I have already explained it. So this one, it is your f bar. If you find that one, this probability that x greater than x is we call it as the f bar x. And if you may go to this one, you can see that for the Pareto distribution, your x bar lambda x is x naught by lambda x to the power alpha. You can write it as which is x by x naught to the power alpha into 1 by lambda raised to alpha. That is f bar x into 1 by lambda raised to alpha, or in other words, you can write your f bar lambda f bar x into g lambda, and so by the definition it is so the Pareto distribution is scale invariant. Okay. Now another concept of interest is the theory of regular variation. Theory of regularly varying. So you see that a distribution f is regularly varying. Regularly varying if the survival function, you may be able to write it as x raised to minus rho into Lx, where Lx is slowly varying. So what does it mean slowly variation, slow variation? So Lx is slowly varying means that Lxy by Lx, the limit as x tends to infinity is equal to 1. What does it mean? It means that Lxy is asymptotically equivalent to Lx. So what does it mean? That is Lx, L2x is in fact equivalent to Lx, L3x is equivalent to Lx, L4x is in fact equivalent to Lx. So, or in other words, the variation in the function within the function L is very slow. So, or mathematically, I may be able to tell that limit extends to infinity, Lxy is by Lx is equal to 1. So, I may say that a distribution function is regularly varying. So, the regular variation, you can see that it is associated with the inverse formula. Right. I am writing my f bar x is equal to x raised to minus rho. Rho is in fact positive. So, what does it mean? So, your f bar x, you can write it as Lx by x raised to rho. Lx by x raised to rho. Lx and what does Lx is? In fact, a slowly varying function. So, you can say that your f bar x is in fact proportional to x raised to minus rho, or in fact, it is, you may be able to approximate your f bar x over the tail of the random variable x by the inverse power law. Right. Such a distribution you may call as a regularly varying distribution. Right. If you have a distribution, or if you have a phenomenon for which you have an associated random variable, and for that random variable you may be able to model with a particular distribution, and the distribution has the probability structure in such a way that whenever x is large, the probability that x greater than x is proportional to the inverse power law. Such a distribution you may call it as regularly varying distribution. And you can see that a distribution is synthetically scale invariant if and only if it is regularly varying. Right. And if you are looking into the deeper versions of probability theory, and if you have looked into the details, you may be able to come across that the what is known as the Karamata theorem and the Tauberian's theorem. And in those situations for modeling the regular variations, you may be able to use these theorems and you can come across the Pareto type distribution. And I have already seen that, told you that the relevance of exponentiality is nothing but the the use of it is that the distribution of the sum you may be able to model by the distribution of the maximum. Maximum in the data set that you can find it. You can find it very easily. But the distribution of sum, finding it is very difficult. But the catastrophic principle tells that the maximum we may be able to model by the distribution of the sum. And it is useful for random walks, queues, etc., where you are looking for the waiting times. And the waiting times in the queuing theory, how you are modeling it, the waiting times in the queuing theory is nothing but the waiting times in the arrival of the customers in regular intervals, in intervals of time. And the waiting times in the intervals of times are corresponding to the arrivals. You may be able to write it as x1, x2, x3, etc. So that the total waiting times is nothing but x1 plus x2 plus etc. plus xn. Or you may a promising customer is interested to know how long he will have to wait in a particular queue before he is entering into the queue. So in that case, he is interested in the distribution of xn plus x2 plus etc. So to find that the sub-exponential case or the catastrophe principle tells that is same as the distribution of the maximum. So it is nothing but it is the distribution of the maximum waiting time of the customer in a particular interval, in a given interval. If you are dividing the total time into a number of subintervals, you may be able to identify the number of customers in each and every subintervals, and you may have to find the distribution of the maximum of the waiting time. Once you know that, you may be able to you may call it as the catastrophe principle. And what is random walk? In the random walk, what you are interested in? Whether if you are looking for the random walk or if you are looking for the Brownian motion process and so on. What we are interested in is in fact the position of the particle after n steps. If a person is performing random walk, or if a particular particle is performing random walk, or whatever it is, what you are interested is in fact the position of the particle after n steps, or the displacement of the particle covered in n steps. What is the displacement of the particle covered in n steps? It is nothing but the x1 plus x2 plus x3 plus xn, where x1 is the displacement covered in the interval 0 to 1, x2 is the displacement covered in the interval 1 to 2, x3 is the displacement covered in the interval 2 to 3, and so on. So you are interested in fact in the distribution of displacement, or you are interested in the random variable xn plus x2 plus xn. So you may be able to study the behavior of that based on the maximum, which is clearly available. So that is in fact the use of the catastrophe principle, which is in fact associated with the self-exponential. And you have the conspiracy principle also. What is conspiracy principle? Conspiracy principle tells that maximum probability of maximum xn, x2, etc., xn greater than t is in fact the order of probability of xn plus x2 plus etc. plus xn greater than t. That is it. What does it mean? So that also you can see that you know the definition. So if a student is studying in the MSc, he may usually study in the very beginning of the course. He will study the notation of small order, small o and capital O. And what I am talking here is the small o. What does it mean? It means that probability that maximum of xn, x2, etc., xn greater than t by probability of xn plus x2 plus etc. plus xn greater than t, that ratio turns to 0 as n becomes large. So that is the result. It is a conspiracy test. And now you can say that the sub-exponentiality, the probability of maximum x plus z plus xn is, you may be able to find it as, what I said, it is nothing but n into probability that xn greater than t. Right. And in what context the sub-exponential distribution first introduced in the literature? The sub-exponential distribution the sub-exponential distribution is introduced in the study of. Is it okay? I am audible or not? Can you hear me?
Yeah, audible, sir. Audible. You are audible. Perfectly audible.
Audible.
Okay.
Okay. So in the case of sub-exponential distribution, in the case of sub-exponential distribution, probability that maximum of xn, x2, etc., xn greater than t, you may be able to approximate it as n into probability that xn greater than t, where x's are i. Correct. So for finding the distribution of the sum, you need only the distribution of x1 and its survivor, and you may not be able to find the distribution of x1 plus x2 plus etc. plus x1. There you can see that it is complicated. Finding the distribution of this one, and you can see that here you are looking for the distribution of the sum itself. But when we are looking for the laws of large numbers and central limit theorem, why we are studying it, and we can see that in each and every situation we may come across xn plus x2 plus etc. plus xn, but the study of xn plus x2 plus etc. plus xn is very difficult, and we can see that in most of the situations you need to make diverse. So that is why we are scaling it. So, and we are scaling it in the smaller units. And so you have your contribution of the individual random variable xn, you are making it as smaller as xn minus a1 by b1. The other one as x2 minus a2 by b2 and so on. So, and then you are looking for the limit. And you expect that in the limit is it may converge. But the sub-exponentiality property tells you that you may be able to find the probability of maximum xn x2 at xn greater than t, which is in fact equivalent to probability that xn plus x2 plus etc. plus xn greater than t is asymptotically equivalent to n into probability that xn greater than t. Right. And also, you can see that in your usual reliability class, you may come across the residual life. What is the residual life? What does it mean? The residual life means that a system performs very smoothly, and it has performed up to time. Then what is the probability that it will perform an additional amount of time given that it has already performed or lived successfully up to time x? Right. So that is but f bar t plus x by f bar t, and you can see that the exponent in the exponential situation, it will give your e raised to minus mu t, which is your memorylessness property, and in the Pareto case, you can see that it will in fact increases in x. Or in general, so this is your MRLF and so on. I am not looking into this one. So heavy-tailed distribution in general tends to have decreasing hazard rate and increasing MRLF. So that you may usually see that it is quite natural, because in the class L properties I have already shown, the behavior of long-tailed distributions is that limit extends to infinity, hx is 0. The limit extends, hx is a quantity which you may have, it is always a non-negative quantity. And the limit of hx is 0 means that the hx should have a behavior that it should be decreasing in nature. And as we expect that in the case of heavy-tailed distributions, it should have DFR, decreasing failure rate, hazard rate. So it is not surprising, it is quite natural from the theory that we have already taught. Okay. Now what I may describe is that I may describe a work of myself on sub-exponential distributions. So I have given a review on the class exponential distributions, what's its implications and so on. And now I will go on to a work which was done by myself with some of my colleagues. One is Dr. Bindu Krishnan, and the other is Professor Hamadani of Marquette University, USA. And this is in fact a paper which has already published in 2020 in the journal Communications in Statistics, Simulation and Computation, where we have introduced a generalization of the Pareto distribution. I have already defined Pareto distribution. Here we have introduced a new generalization of Pareto distribution, which is in fact a class of distributions that contains Pareto. And the Pareto, you know that Pareto has a regularly varying distribution. Pareto is in the class of dominator variation distributions. Pareto is in the class of long-tailed distributions. And Pareto is sub-exponential, and so on. So what we have done is that we have introduced a new class of distributions, which is again falling within this framework. That is, which is again sub-exponential. So I may just explain how we have introduced the distribution. the introduction of the distribution is in fact the way of introducing it is in fact so natural. Hello, sir. Hello. അതിൻ്റെ ഇപ്പം തന്നെ തീർക്കാം, ഇപ്പം നിർത്താം, തീർന്നു ഒത്തിരി. Okay, I have arrived only up to 12 slides out of 43 slides that I have prepared. Okay, so I have able to complete only 1/4 or less than that. But I think that in this talk, my main intention was the concept of sub-exponentiality and heavy-tailedness is newer to a number of participants, and I think that I have given a little motivation on this, the class of sub-exponential distributions, its importance, its role in the existence in our area and so on. And if any questions or clarifications, please ask. So I am concluding my talk. If any questions or clarifications, please ask.
The discussion is open for clarifications. If any doubts the participants have, please clarify. A small clarification.
Hello.
Hello.
Hello. I am Dr. Muhammad Jahangir Ali, Al Buremi University College, Oman. I am an associate professor and academic dean also. So we are conducting the graduation project. So which is the most important tool for statistical method we have to apply, like a t-test, ANOVA, regression analysis, like a correlation, mean, like this. These are different statistical methods are there. Which is the more appropriate for the data analysis?
Hello. So that question need more and more discussion, because the situation may be different based upon your requirement. So based upon your data and what are the types of work that you are conducting, what is the type of clinical trials that you are conducting, or what is the type of the lifetime experiments that you are conducting, whether you are getting a huge number of data sets, whether the data sets are in fact dependent data sets, or whether they are the independent data sets, and so on. Based on that, you may be able to identify in some situation you can see that your t-test may be approximate. If the number of observations may be large, you may be able to use the normal test. And if you may not be able to know the distribution itself, then you may be able to use for some non-parametric tests. So all those things will depend upon the situation. Okay. Thank you for it.
Okay, thank you very much.
Thank you very much.
I hope this answers your question. Any other question? Dear participants, if you have any queries, you may ask now. It looks like we have covered all of your questions. Now, I invite Ms. Mary Priya to deliver vote of thanks. Over to you.
Good afternoon, one and all. On behalf of the Christ College Autonomous and Department of Statistics and everyone who is gathered in online platform, I would like to extend my gratitude to Dr. K. Jayakumar for an enlightening session on sub-exponentiality and integrated tails. The point where Dr. K. Jayakumar told us about the sub-exponential distribution and heavy tail was really informative. I am pretty sure the precious knowledge that Dr. K. Jayakumar gave us will definitely help us in our studies and future. Once again, I would like to thank Dr. K. Jayakumar for taking out time from their busy schedule and enlightening us with the knowledge. Thank you so much, sir.
Thank you, Mary Priya. Now, we are entering into our second technical session. I invite Dr. Sister Mariama to introduce the speaker. Over to you, sister.
We have the second session by Dr. David Hanegal, Professor and Head of Faculty, Science Vishwakarma University, Pune, and former Professor and Head SP University, Pune. He was an elected Fellow of Royal Statistical Society, London, UK in 2003. He has more than 40 years of very active teaching and research experience in inference, in bivariate and multivariate exponential distribution, survival analysis, frailty models, etc. He has received many appointments from various reputed universities of Mexico, Germany, USA as a visiting professor. He is the author of 100 plus international publications with nearly 800 Google citations and very good impact factor. The books written by him were published by very reputed publishers like Taylor and Francis, etc. He is referee for various journals like Communication Statistics, Biometrics, Statistical Papers, Journal of Multivariate Analysis, and so on. He is life member of many national and international academic bodies. He has delivered talk in more than 50 international conferences and have undertaken many research projects funded national, international universities. Today, he will talk about positive stable shared frailty models based on additive hazards. May I now request you to, sir, to handle this session.
Hello.
Yes, sir.
Hello, I am David Angel. Whether I am audible?
Yes.
Yeah, audible.
Yes.
Okay. Can you see the screen?
Yes.
Can you see my presentation?
Yeah, before seminar.
Can you see my presentation?
Yeah, you can see the screen of all the files in the folder. Before seminar is in tick status.
Okay, okay.
Okay.
I'll just click this one. Where is that one? Okay, new share. I can just say. There are some basic, advanced, and files. Where I go basic. Can you able to see the presentation?
Yeah, we are able to see only the total files in the folder. That file selected is a P4 seminar. That is your desktop, I think I am seeing.
Okay, P4, that is not open, I think.
Yeah, it's not open.
Okay, just I want to open. Okay, just say resume share.
Yeah, it's okay,
Yes,
sir.
it's
Open.
okay.
You can see it, no?
Yeah,
Yes,
sir.
yes.
Fine, it's fine.
All right, I'll just open from my side. Why it's not opening? Okay, I'll just minimize this. Okay. Can I make full screen?
Yeah, screen is visible, sir.
Okay, that is completely visible, no?
I think you have to maximize it.
Maximize. Okay.
Yeah.
I'm just checking. Where I do.
It is in the top right corner, it seems.
View, okay. Full screen mode.
Yeah.
That is okay now?
Yeah, okay, sir. Very good.
Okay. Thank you very much for inviting me as an invited speaker for the webinar conference. I thank the organizers for the invitation, and it's my pleasure to be here for this webinar conference. The topic I'm going to talk today is positive stable share variety models based on additive hazard. Now, this is a branch of survival analysis. You may be knowing some survival techniques, survival models. Mainly, it contains censored observations. Many times we can't observe the entire observation in the samples. Some part of it we can't observe it because of some technical problems, maybe lack of time, or sometimes it may be very expensive to obtain entire sample from the sample, or one has to take a very long time to observe up to end of the sample. Maybe, for example, if you take patients, cancer patients, AIDS patients, asthma and other things, they take a very long time. You can't wait for a long time. The study will be for 5 years or 10 years, some limited period. Then you have to give the decision based on your data, whatever data you have collected. This is sensor data. It's not actually, it is a censored, maybe at the left censored or right censored or interval censored, different types of censoring are there. It is a different from truncating. We are not truncating anything. We are just censored. In the truncated, it is a complete data. But in the case of censored data, it is complete, incomplete data, censored at right side or left side, or interval censored different. Even current status data is also censored data and other things. I think you understood what is the meaning of this censored data. Now, what is survival data? Survival data is a time to event data. The event may be either death or failure or cause of infection in the patients, or some in the mortality data, it is just death. But in the case of employment data, you can say it is once a job is taken place from somebody, then it is an event. In the marriage data, once the marriage is occurred, then it is an event. And employment data, marriage data, different types of events are possible, not necessarily the failure or deaths. It may be any event. Okay. This is a time to event data. And mainly there are different types of techniques involved. One is we use the estimate, survival estimate, using Kaplan-Meier estimators, and taking that is completely not based on the model. Okay, based on the data you collected, we just estimate it. That is a non-parametric. One can also have survival curve based on the model itself and non-parametric also. Okay. Now I explained what is survival analysis. Now shared variety model. See, in the case of patients in the hospitals, If all patients are in the same hospital, they share the common risk within the hospital. The lab is same, the doctors, nurses, staff, everything is same. They share the common risk in the hospital. That is called shared frailty model. The heterogeneity involved in the hospital, that is called frailty, that is shared by all the patients. That is shared frailty model. Suppose if I take the data from different hospitals, then it will be a heterogeneous data. That means the hospital centers have different doctors, staff, lab, operation theater, and all of the risk differ from hospital to hospital. Then the risk is not common. It's not shared by all the individual patients in the data. That is a heterogeneous data. In that case, we can't use shared frailty models. There are different types, we can't use the usual Cox model. We have to use the frailty models for that. That is different for different hospital centers. Not necessarily hospital, if you take family, patients with a different family backgrounds or patients with a different family, they have different risk. They don't share the common risk because they have different family backgrounds and different genetic factors. In that case, there is some heterogeneity in the world. Then in that case, we have to use shared frailty models. Okay. Now I'm just going for the basics. I start with the Cox proportion model that is given by equation number 1, that is given by Cox in 1972. The hazard rate given x is the explanatory variable, covariate you can say, that is equal to H naught T. H naught T is baseline hazard at time t greater than or equal to 0. X is a vector of explanatory variables and beta is a column vector corresponding to regression coefficients. This is a multiplicative model. Here this quantity exponential x prime beta is multiplied with H naught T, baseline hazard. That's why it is called multiplicative model. Okay. This is given by Cox in 1972. Yeah, the basic assumption is there is a homogeneity of the subject in the population, which is somewhat questionable. I just give an example, different centers, genetic factors and other things are there. And these are heterogeneity involved in the data. Okay. If this is the case, then we can't use this model, this Cox model, equation number 1. Okay. If there is no heterogeneity, then you can use this model, Cox model. In case there is a heterogeneity, then we can't use this model. Then we have to modify this Cox model into adding a heterogeneity factor. That will come later. Okay. Now, what are the reasons when sometimes we neglect the covariates? What are the reasons? We can't include all the covariates in the model. Some covariates are very useful, even then we don't know. It's not possible to measure. Sometimes we neglect it. And we don't know the importance of the covariate and we sometimes neglect it. Or we just remove from the analysis. Okay, what are the reasons? If there are too many covariates to consider, in that case, we just take some covariates. Lack of appropriate tools to measure the covariate. Sometimes it's not possible to measure. Then we drop that covariate. Researchers are not aware of influence of the potential covariate that might exist. For example, existence of genetic factor or environmental factors. Just now I gave the example. It is not possible to measure sometimes, or we are not aware of this covariate. In that case, we just ignore it. Okay? not all necessary coefficients are included in the model, which modify the distribution of survival time and makes the model parameter biased. When we exclude the important covariates or factors, then the model parameters will become, estimate of the model parameter will be biased in that case. It may be underestimated or overestimated. That will, then whatever model we have chosen, that will be inappropriate in that case. Therefore, we need to introduce some random variable that accounts for the neglected covariate. We have to introduce some random variables, that is in terms of a variety or heterogeneity, characterizing survival changes due to individual variation, which is apparently unobservable. A variety is unobserved random proportionality factor that modifies the hazard function of an individual or of related individual. Clayton was the first one to observe this random heterogeneity, random covariate in the multivariate survival data on the chronic disease incidence in the families without using the notion. In the year 1979, Weipel took the univariate survival. He introduced this term variety that time, first time. Variety is the extension of Cox proportion model that I just now explained. In addition to the observed regresses, a variety model also accounts the presence of latent multiplicative effect of the hazard function. But if this effect or variety is not directly estimated from the data, but is instead assumed to have unit mean and finite variance, which is to be estimated. This shared variety parameter is due to some genetic factor or environmental factors, which are unobserved in an individual and are common and shared by both paired organs in human and twins in the family. This shared variety model, the parameter is also responsible for the dependence between the two components. Okay. If the variety is significant, this is if we ignore the effect of variety, what is going to happen? If the variety is significant in the model and is ignored, then the model will be inappropriate. The decision based on such model will be misleading in that case. You can do the analysis and all other things, get the results, but the analysis will be wrong in that case. If the variety is ignored, the estimate of regression coefficients will underestimate or overestimate. And you also obtain the model selection criteria, AIC, BIC, DIC, which will be more as compared to the model with variety. Unnecessarily, these quantities will increase. When the model is wrong, these three quantities will increase. But for the good model, you must need AIC, BIC, DIC to be minimum in that case. The decision based on the model without variety will go wrong. The ignoring the variety effect with finite mean may result in negative bias in the estimated time dependence. In general terms, we let heterogeneity go into error term. This will, of course, lead to an increase in the variability of the response as compared to the case when the variety is included. That is the main things. These are the things that is going to affect when variety is ignored. Okay. Now I am going for the model. Okay. I just explained the multiplicative model. Now I am explaining the additive model. Yeah, if the variety acts additively on the hazard rate function, in such situation, a univariate variety model is derived below. A continuous random variability lifetime of an individual. Allen proposed in which COVID acts additively on the baseline. The model is given by this one, given by Allen. See, earlier what I wrote, it was a multiplication here. Okay. Instead of multiplication, now it is addition. This is additive model. Okay. One can also write in this way. Okay. This plus x prime beta, I can write it as e raised to x prime beta. Okay. Here, this term is minus infinity plus infinity. And if I take e raised to this term, then it will be 0 to infinity. It will be 0 to infinity in this case, plus. Okay. Then hazard, given the Z. I am introducing a Z. Z is a variety here. Okay. That is written as what I am adding this term. U beta U. Okay. Earlier it was only addition of e raised to x beta. Now I am adding U beta U. Okay. U is unobserved covariate and this beta U is a corresponding regression coefficient for corresponding to U. Okay. This is addition. This is an unknown quantity. This is a random quantity. Okay. That means e raised to U prime beta U. That is a random quantity because U is random. Now this I can write it as Z. E raised to U beta U as Z. That is here. Okay. Now Z is your heterogeneity, that is called variety. Okay. You know, U is minus infinity plus infinity, then Z will become 0 to infinity in that case. Okay. Okay. Now you can relate cumulative hazard function and survival function. Okay. That is also that. Before that, you can just take integrate over the previous term. Integrate over this term, you get cumulative hazard. This will become capital H naught T, and this will be a independent of T, therefore it is T into this one. That is here. Okay, that is a term, cumulative hazard. Now relate cumulative hazard and survival function. There is a relation that you can write it in this form. This cumulative hazard. That is here. Whatever is written, that same term is there. Okay. And this is a survival function of T given Z. Z is a variety. Z is given here actually. But it's a random variable. One can integrate over Z, you get survival function of the Z. Now integrate over Z, because Z is random variable, integrate out. It has some density of Z, that is this one, and integrate and you will get this term. Now this term, okay, e raised to minus ht, that is independent of Z. You can take it out and remaining term is e raised to minus zt, this one, that is here. This is a Laplace transform with argument t into e raised to x prime beta, that is the term. Laplace transform of random variable Z. Okay. Now this is the term after integrating over Z. Okay, that is the thing. That means you can express survival function in terms of Laplace transform. Now earlier I have taken the univariate. This is univariate. If it is a bivariate, okay, take for example bivariate component, say paired components in a human being, for example, lungs, kidneys, eyes, all these are paired components. If you take T1 and T2, okay, so two component system, you can have a bivariate survival function based on this. Now what I'm taking Z1, Z2, okay, Zj, okay. This Zj is a heterogeneity, that is variety, and that is given Zj, then these two are independent. Okay, that is here. You can write S of T1 and S of T2. given ZJ and ZC. That is here. Okay. Here you can separate out T1 and T2. Okay. Because it is given Z. That is this one. Now integrate over Z. Okay, this term is the survival function. Here you can separate out T1, T2. Integrate over Z, then you will get this term. Now this term, you can't separate out T1, T2. That leads to dependence of T1, T2. Okay. Earlier T1, T2 are independent. When you integrate out, then this T1, T2 will become dependent because Z is shared between T1 and T2, both. That is a common risk for both T1, T2. Therefore, this T1, T2 will become dependent. And this is a Laplace transform of the priority variable ZJ for the jth individual. That is this one. All right. Now, I have not defined what is priority density function. Okay, there are different types of priority models. This f of z, you can have either gamma priority, inverse Gaussian priority, positive stable priority, power variance function priority, compound Poisson, compound negative binomial, piecewise gamma, correlated, additive, different types of priority models are there in the literature. Okay, we already have paper in the gamma and inverse Gaussian for the additive model as well as multiplicative model. The usual hazard, one can have reverse hazard, different types of models are there. We have a series of papers on these with usual hazard and reverse hazard for different priority distributions. And one can have, instead of Z, you can have Z1 and Z2. Then Z and Z2 are correlated priority models. Okay. Instead of just common risk, we can have different risk. For T1, Z1. For T1, you can have priority as Z1. For T2, you can have priority Z2. That is also possible. Okay. Now in this paper, we only mainly focus on positive stable priority model. Okay. Now there are a lot of importance on the positive stable priority as compared to gamma and inverse Gaussian. There is a lot of literature already mentioned. Hogarth in the book as well as in his several papers, he has mentioned what are the advantages of positive stable priority over gamma and inverse Gaussian and other priority models. Okay. I'm not going in detail the advantages. Just mainly focus. These are the different authors. Okay. Sometimes the gamma priority may not fit well that they have already shown. Positive stable is a useful alternative in part because it has attractive features that predictive hazard ratio decreases to 1 over time. This property is observed in familial association of ages on onset diseases with etiological heterogeneity where genetic cases occur early and long-term survivors are weakly correlated. Okay. This is the literature. Now, what is the PDF of positive stable distribution? Okay, this is a positive stable distribution. Okay, the density of the function. The main thing is here to take care of this is stable distribution. The density won't exist on the real line. Okay, it's not on the real line, but you can write the density in the form. The Laplace transform has the closed form. Okay, that is this one. Yeah. when there is a problem of identifiability in the case of when you introduce variety models. In order to resolve this, we have to do some restriction on the parameters. This restriction in the case of positive stable is alpha delta equal to theta. I'm just reducing one parameter. Earlier there are two parameters, now it is one parameters. Only one parameter. Now the new density will reduce to this one. Okay. And theta is between 0 and 1. With the Laplace transform, this is the term. Okay. Now, under the assumption of independence, the bivariate condition survival function given the variety z at time t, t1, t2. Okay. So bivariate one, that is here. Given z, both are t1, t2 are independent. That is here. Okay. We get unconditional bivariate function for z, that is this one. When you integrate over z, we get unconditional, that is here. Okay. This term is here, and f of z is integrated. Okay. That is here. This is the expression, it is already given earlier. Okay. Now I am using what is a Laplace transform of z when z is positive stable, is just this whole argument raised to theta, that is here. E raised to minus this whole argument raised to theta. Okay. Now, earlier when you see when given z, these two we can very easily separate out t1, t2 here. After integrating out, you can't separate out t1, t2. There is a dependence between t1, t2. When theta equal to 1, then t1, t2 are independent. Okay, in that case, when theta equal to 1. That is the thing. That means that is a degenerate in that case. The z will become degenerate when theta equal to 1 in that case. Okay. In the absence of covariance. That is this one. Okay. Now I just take baseline distributions. I'm taking completely parametric approach. One can also have non-parametric. T1, T2 are non-parametric. And that can also be done. Now take, here in this paper I'm taking parametric approach. I'm taking two baseline distributions, generalized log logistic and generalized Weevil. Okay. The log logistic distribution survival function is this one. Okay. That is, I'm just generalizing this log logistic situation. I'm just taking the log logistic distribution, okay, this raised to alpha. Okay. This is called Lehman family. You can refer Deshpande 2005 in his book, Lifetime Distribution. Okay. Yes, not very any arbitrary known survival function. If alpha is positive, then this is the term. Okay. Lehman family. Okay, just take 1 minus survival, then that is distribution function. Then cumulative hazard, then hazard. Just to differentiate this, you get this term. Okay? That is hazard function. If gamma is less than or equal to 1, failurity is decreasing. If gamma is greater than 1, then failurity is increasing. Now the second one is generalized Weevil. Okay, you know the Weevil distribution that is here. without taking alpha, excluding alpha, this is a Weibull distribution. Just take raised to alpha. Weibull distribution raised to alpha, that is called generalized Weibull. Okay. Like exponential distribution, you just take distribution function of exponential raised to alpha, you get generalized exponential. The same way, this is generalized Weibull distribution. And this is a cumulative hazard. Differentiate this with respect to t, you get hazard function. And gamma equal to 1, alpha equal to 1, this is exponential. And gamma is not equal to 1, alpha equal to 1. This is Weibull. Gamma less than 1, alpha less than 1 is decreasing, and gamma greater than 1, alpha greater than 1 increasing. Failure rate is increasing. Different possibilities are there. When parameter alpha takes different values, you get the different failure rates, increasing, decreasing, but unimodal in the different types of failure rates are possible in the generalized Weibull. That is the advantage. You can take care of all the possibilities. Okay. Now substituting cumulative hazard function for generalized law logistic generalized Weibull in the unconditional bivariate survival function, we get corresponding bivariate survival function. I am just substituting the cumulative hazard function in the equations, earlier equations. Which equation I'll just show you. The unconditional bivariate survival function that I have given earlier. Let's go back. Here, this equation. I'm substituting this H0 1T1J, H0 2T2J. Other things are as it is. Only these two quantities are substituting. Then you get this equation. Okay. This is for generalized log logistic. Cumulative hazard function I am substituting here and here. That is for the generalized log logistic. And here, this one and this one. This is for generalized Weibull distribution. Okay. H1T and H2T. Okay, these two distributions. 7 and 8. And 9 and 8. What I'm doing, I'm taking 4 models with 2 baseline and with variety and without variety. With variety there are 2, without variety there are 2. With the 2 baseline distribution in all 4 models. That is 7, 8, 9, 10. These are the 4 models. Okay. Here it is 7, 8, 9. The number has some mistake in the number. 7, 8, 9, 10. That is the number. 7, 8, 9, 10. Okay, these are models. Model 1 and 2, 3, 4, 4 respectively. 1 and 2 are for generalized models with variety and without variety. 2 models. Likewise, 3 and 4 are generalized Weibull distribution with and without positive stable variety model. Okay, these are. I am just denoting model 1, 2, 3, 4. And using the Bayesian approach to estimate the parameters. One can have classical also, classical estimation. Sometimes there will be problem using the classical estimators because the estimators, MLEs, whatever you obtain, they are not in the closed form. You have to do iterative procedures, Newton-Raphson procedures, and sometimes the Newton-Raphson procedures, they won't merge in the iterative procedures, and that problem will come, and you can't resolve that iterative procedures, and you can't obtain the MLEs. When the data is small and the censored, then there will be always a problem in estimating the MLEs through the ITT procedures. One can go for Bayesian estimation, and there will not be any problem when the data is small and censored. You don't face any problem in the Bayesian estimation. Only thing is it will be laborious procedures. The lot of ITT procedures, techniques are involved, Metropolis hastings, Gibbs sampling, so several things are included in this Bayesian approach. Now, take a sample of size n, okay, and you get first and second difference time, T1 in T2, because it's a bivariate data, and censoring time, left hands. Now, how do you write the likelihood when in the bivariate censoring? Okay. In the case of bivariate censoring, what happens? There are four possibilities. Okay. Both failures, T1 and T2, both failures of the first component and second component are observed. That is the first case. That is here, F1. Both T1, T2 are observed. Second case, only first failure is observed. Second one is censored. That is the second possibility. Third one is, first one is censored, second one is observed. Failure is observed. And both are censored. No failures are observed. These are the four possibilities in the bivariate censor. Okay. Then your likelihood will be split into four parts. If the sample size is n, suppose this is n1, n2, n3, n4, and sum of n1, n2, n3, n4 is n. Okay. That is the way you have to distribute the likelihood. That is a form. You can write likelihood in this form. Okay. N1 is the number of observations corresponding to this reason, first reason. N2 is the number of observations corresponding to this reason. N3 is the number of observations corresponding to this reason. And N4 is the corresponding. So both are censored, no failures observed. That's it. Okay. This is a likelihood. Now, how to obtain F1, F2, F3, F4? This is the formula. When both are failures, then it's trivial. You have to differentiate S is of T1 and T2. Only T1 first failure is observed, that is T1 is observed, T2 is censored. Then you have to differentiate only with respect to T1. That is here. When the second component is observed, failure of the second component, then you have to differentiate only with respect to T2. And both are censored, then there is no need to differentiate with respect to T1. That is censored. Before going to the kidney infection, we did the analysis, this Bayesian approach, using the simulated data first in order to see the performance of the estimate. And we saw the performance of the estimates are very good, and the SE and all of the other components and KVK test and other things, Gulben test and other things, all are doing excellent job. And after that, we did kidney infection. I just omitted that analysis part of the simulation data. But I'll give the tables of simulated data. There's no problem. I can show the data. Now, what is this kidney infection data? It is a sample of 38 patients. Okay. Kidneys. So biureter, there are two kidneys in the human body. First kidney and second kidney. The recurrence time of first recurrence, second recurrence times in days. That is observed. Okay, therefore, there is a infection from time to insertion of the catheter until it has been removed. Owing to infection is recorded. A catheter may have to be removed for the reasons other than kidney infection. This regarded as censoring. So the survival time of a patient given may be first or second infection time or censoring time. After the occurrence of censoring of the first infection, sufficient time was allowed for the infection to be cured before the second time catheter was inserted. The first and second recurrence time are taken to be independent. This is the data. It has T1, T2, and 5 covariates are there that we'll see. What are the risk variable or factors? Age, sex, that is gender, male and female. There are 3 types of disease: GN, AN, PK. The short form of GN is glomerulonephritis, and AN is acute nephritis. PKD is polycytic kidney disease. Okay. I'm just taking this 3 types of disease, presence and absence. Okay. T1, T2, these are the first and second, and these are all 5 covariates. Okay, and we check the goodness of the data. All right. Now the proportional hazard model is this one. There are 5 covariates, and it's the variety, heterogeneity, baseline hazard, and this is the terms. Okay. These are the indicative variables 3, X3, X4, X5. And X1, X2 is also. That is male and female. Only X1 is a continuous covariate. Now give the tables and graphs. Okay, this is a simulated data. Before taking the kidney infection data, we did simulation in order to check the performance of the estimators. See, parameters assumed. These are the parameters assumed. Okay. And then we estimate it. Okay. We taking this as a simulated data, assuming this as a data, then estimate. They are close to the true values. The estimates are very close to the true values. Standard errors, lower credible intervals, upper credible intervals, KVK values, P values, Gell-Run values. The P values are very close to 0.5. KVK values very close to 0. And Gell-Run values are close to 1. Yeah. This is the one. Similarly for model 3, I am just doing the simulation results for model 1 and 3 because 2 and 4, they are without frailty. There is no frailty involved. The frailty term is theta here, 0.5. Here it is 0.5. We have taken. Similarly, we did for the model 3. Okay. This is generalized variable. There is a misprint, I think. It's not the first question. It's supposed to stable. It's a mistake. It's supposed to stable model. Okay. Okay, now posterior summary of the kidney infection data. Okay. Now see the estimates of the parameters, standard errors, lower trivial intervals, upper trivial intervals, inequalities. Now theta is 0.62. It's significant. Theta takes value between 0 and 1. 0.62. Okay. If theta equal to 1, then there is no priority. Okay. These are the standard errors and all things. Just check the covariates, regression coefficients. Okay, this beta 2, both lower and upper trivial limits, both are negative. And beta 5, the lower and upper trivial limits, both are negative. And the estimates are negative. Now, what is the interpretation of this one? See, this is significant because this doesn't include 0. Because both are negative means it doesn't include 0. Here also, both are negative means it doesn't include 0. In all other cases, here it includes 0, this includes 0. Beta 1, beta 3, beta 4. The regression curves, lower and upper, they include 0. Only beta 2 and 5, they don't. Because this shows they are significant. And what is the interpretation? Beta 2 is the gender effect, okay, male and female. That means females have lower risk of infection as compared to male counterparts. That is a mean. Okay. And this beta 5, okay, this also have lower infection when there is an absence of the disease type 3, PAD, that is a mean. Okay. This is for the model 1. Model 2, this is a without priority. There is no priority. Theta, there is no theta in this. Okay, let us see the covariates effect. Beta 2 is still, both are negative. The significant here. That means 0 is not included. Beta 2, that gender effect is significant. That means females have lower risk of infection as compared to male counterpart. This is model 2. Okay, this is for with generalized losses. Model 3, this is for the positive stable model with generalized people as a baseline. Model 3. Theta is 0.7. Now, what we observe from the parameters, the regression parameters, beta 2 and beta 4. These are significant here. When you take model 1 and 3, we have similar result, decision. Beta 2 and beta 5 are significant, and the decision is same. Okay, in that case. Okay. Beta 2 is significant and beta 5 not significant. Okay, model 2 and model 4 are somewhat similar, the results, without priority. And this one, this is without priority, and baseline is generalized viewable. Okay. Now these 4 models I have analyzed, okay, using the kidney infection data. Now, all these are fitting to the data anyway for this. Okay. This is the p-values, okay. Then you see the fitting of the data, the kidney infection data. T1, T2 I have taken separately. The p-values are high. That means this model supports the data in this case. The model is it supports. All these 4 models supports. And now how to take a decision? Which model is better out of these 4 models? Okay, which model out of, then in that case, we have to see the comparison of these 4 models. Okay, comparison of these 4 models. 1, 2, 3, 4. Just now we discussed. AIC, BIC, DAC. Whichever is minimum, that will be the better model. Okay. The positive stable with and without fault. 628. Positive stable with and without faulty. Generalized Weibull model. Model 3. 622. 622 is less here as compared to all these. 645 is less as compared to all these values. 624 is less as compared to all these values. Now, out of these 4 models, whatever we discussed, in that 622 is lowest, 645 is lowest, 624 is lowest. That means the positive stable model with generalized Weibull as a baseline is better than all other proposed model, the 3 proposed models, whatever we have considered in this paper. I am also considering this comparison of this model with earlier models, in my earlier paper, gamma variety and inverse Gaussian variety. Gamma variety with log logistic and generalized Weibull, inverse Gaussian, generalized logistic, inverse Gaussian, generalized Weibull. Here I have AIC, BIC, DAC. But all these are greater than 622. And these are all greater than 645. And these are all greater than 624. That means our proposed model positive stable variety with generalized Weibull as a baseline is better than all existing models. That is the meaning. One can also have base factors. One can decide which model is better. Here we have to compare between the 2 base factor, numerator and denominator model. We have to take the numerator is posterior density of the model 1 and model 2, for example, this one. That is the thing. The base factor, the ratio gets taken. See, all are greater than 6 almost. This is minus. That means this one is better in that case. When it is minus, then instead of 2, you have to take 4 in that case. That's all. Just reverse it. Model 4 versus 2 is means 7 point something plus 7 point something. Okay, anyway, compare between our models. Now, in all the cases, model 3 is better. Here, model 3, model 3, model 3. That is better. Model 3 versus model 3 other models are always better than other models. It's model 3 means positive stable variety with generalized Weibull as a baseline. Now I am comparing the AIC, BIC, DAC in the positive stable variety models. What I'm doing here in this table, I'm comparing additive models with the multiplicative models. Okay, we have different multiplicative models for the positive stable model. I'm comparing this model with positive stable multiplicative model. These are already discussed in my earlier papers. I'm just writing the values of AIC, BIC in this table. Okay. These are all positive stable models. Only thing is some first two are additive. It is given in the present paper, and these are in the previous papers. Okay, all these things. The baseline are different baseline: generalized, log logistic, generalized Weibull, weighted exponential, extended Weibull, Pareto distribution, linear favorite. These are different baseline distributions, non-multiplicative model. When you see this model and AIC 622, I think this is the least among all these. 622 is the least. That is our model 3, the proposed model. And 645 is the least among all these. 624 is the least among all these. And here also we can conclude that the positive stable variety model with generalized Weibull is better than all the existing models. Okay? In the proposed as well as the earlier existing models. That is the decision. I'm just taking the graph fitting. We did the Kepler-Meyer case estimate and p-value also. It's a graphical fitting. The Kepler-Meyer estimator and the usual Serval fiction model, using the model and the non-parametric. Both are very close. The fit is good in here also, in the graphical. For the model 1 T1 T2, model 3 T1 T2. This is for the Friday. That is the thing. And one can also have the analysis based on the semi-parametric, that is taking a baseline as non-parametric. That is also there. And one can also have the dependent covariates. Okay, one can also have, there is a literature on dependent covariates, that is also there. One can also have dependent covariates. And we have also literature on the priority when Z is a stochastic variable, non-stochastic, stochastic process. So far we have taken random variable, one can have Z as stochastic process. That is also some work is also already done. That is called Levy process. Priority models based on Levy process. There are a lot of literature already there. I have a book, first edition on the priority models in 2011. The second edition has out in the, just last year, 1 year back, the Springer on the priority models. One can refer the book also. A lot of details are all discussed, different types of variety and the different varieties of baseline and other things. All are discussed in detail. I think I will stop here. If you have any questions, I'm very happy to answer. Thank you for giving an opportunity to share my ideas in this webinar conference. Thank you to all. Thank you.
Thank you, sir, for giving your valuable insights. So with that, we will go ahead and take some time for questions. Dear participants, you may ask your queries now.
Hello.
Hello.
Yes.
Yes. Very much thank you, sir. I would like to express my thankfulness to you, sir, and great lecture, sir. Actually, okay, sir. And really, it's very nice lecture, sir, you have. and due to some technical issue, I left some your lecture, but our field research area in Bayesian inference, sir. So I want to how to choose the prior for the these are the models.
Here we have taken gamma prior, okay, and uniform prior, these two priors, but it is independent of the priors, whatever prior. One can also improper prior, some conjugate priors and other things. Different types of priors are there. But in our case, it doesn't depend upon the prior. That is the distribution.
Is there, sir, some rules for the data as to how elicitate the priors? Is there some?
See, for the usually the scale and the location scale parameters.
Yes, sir. Yes.
Gamma prior. Okay.
Yes.
Usually for the scale parameter, we take the gamma. One can also choose the other also, uniform prior and other things. But in our case, now what we checked both the priors, okay, and it doesn't affect whether you take this prior or that prior.
Okay, sir. Okay.
Thank
okay,
you, sir.
Very much thank you, sir.
Okay, Dr. Manoj, sir,
Yes.
can you please introduce yourself?
Yes, I self Dr. Manoj Kumar. I'm assistant professor in Central University, Haryana right now. And I teach here a statistics department here. Near about 4 years from here. And
Okay,
I know David Hangal sir is very nice personality.
Okay, sir. Okay.
Okay, ma'am.
Okay, thank you, sir. Thank you.
And your organization very you actually there is some technical issues here. Some that's why I miss some lectures.
Okay, sir. Okay, sir. Sir, YouTube link is available. You can
Yes.
access that.
Okay, ma'am.
Okay, sir. Okay. Thank you.
Okay, ma'am.
Any other queries? Any other queries? Hope there is no more queries. So let's come to an end. Now I invite Dr. Bindu PP, Assistant Professor, Government Arts and Science College, Minchanda, to deliver vote of thanks. Over to you, ma'am.
Good afternoon, one and all. Respected Professor Dr. David Hanagel, sir, former Professor, Department of Statistics, Savitribai Phule Pune University, and Professor Dr. K. Jayakumar, Head of the Department of Statistics, Calicut University, Dr. Davis Anthony, sir, Head of the Department, Christ College, Iringalakuda, eminent professors across the world, research scholars, and students. It is my pleasure to extend a vote of thanks to our eminent speaker, Dr. David Hanagel, former professor of statistics, Savitribai Phule, Pune University. And we are lucky to have you, sir, today evening. And today, Professor discussed most recent work on positive stable shared frailty models based on additive hazards. And in this talk, he discussed in details about positive stable shared frailty models with the different baseline distributions, generalized log logistic and generalized viable distribution. He discussed in details the estimation procedure and applications in for kidney patient data. It's very useful, sir. It is very useful, and also I found that this area of research has a lot of applications in survival analysis and biomedical research. And I hope all of us are benefited from your excellent talk. And really, your talk is very interesting and fruitful one. And behalf of the RISMA 2021, and I would like to extend my heartfelt thanks to you, sir, for spending your valuable time with us and also sharing your wonderful knowledge. And I am sure the researchers, budding researchers and students will be benefited out of this program. Thank you, sir. And also I would like to thank Department of Statistics of Christ College Iringalikuda for organizing wonderful program like this. And because of this, we got opportunity to listen to Professor K.J. Jayakumar and Professor David Hanagel, very eminent personality, and it's a very encouraging talk. And thank you all. Thank you very much.
Thank you, ma'am. Thank you, ma'am. Dear participants, kindly note, feedback link is now available in chat box. Once again, thank you all for participating in today's webinar. Hope to see you all again day after tomorrow, that is on 25th February 2021 at 2 p.m. Once again, thank you all. Thank you.